For most of human history, space seemed simple. You opened your eyes, and there it was, a stage with length, width, and height. You could draw lines across it, build cathedrals in it, or throw a rock and watch it arc through the air. Space was unquestioned. It was the container of all things, and geometry was its law. In the 19th century, geometry was considered sacred, a mathematical gospel chiseled into the foundation of reason itself. The principles set down by Euclid in ancient Greece, lines, angles, parallel rules, were seen not as clever models, but as unavoidable truths. They weren't just how space behaved, they were what space was. It was the geometry of the gods. But then came a crack, a small, silent fracture that began not in the stars, but in the minds of mathematicians. What if, they wondered, Euclid's fifth postulate about parallel lines never crossing wasn't the only option? What if, instead of one geometry, there were many? Strange geometries where the sum of the angles in a triangle was not 180 degrees. Worlds where parallel lines curved towards each other, or drifted apart. Could such a thing even be real? It turned out yes. These weren't just clever puzzles. They were logically consistent systems, complete in themselves. You could build an entire geometry, an entire reality on different axioms. And if space could obey different rules and still make sense, then maybe geometry wasn't a divine truth after all. Maybe it was a tool. That realization shattered something, because once you let go of the idea that Euclidean geometry is the only path, everything begins to shift. Curved space, bent space, warped space, it all becomes possible. Space is no longer a rigid grid, it's a playground. And the man who opened the gates to this playground was Bernhard Riemann. In a single, quietly delivered lecture in the mid-1800s, Riemann reimagined geometry not as a single universal truth, but as a family of possible spaces. He introduced the idea of manifold spaces that can have any number of dimensions, curved in any direction, with local rules that may not match our everyday experience. The number of dimensions, Riemann said, was not some divine constant handed down from the heavens. It was a choice. Just like a painter chooses the size of their canvas, we can choose the number of dimensions in our space. This was revolutionary, because now, asking, how many dimensions does space have, was no longer a philosophical musing. It was a scientific question, one that could be tested, explored, and maybe even extended. Before we climb further into this dimension warping rabbit hole, now's a good time to breathe. If you're enjoying this journey beyond what feels intuitive, please consider subscribing or liking. This helps bring these quiet, strange ideas to more curious minds like yours. So, let's go deeper. Right now, we live in what feels like a three-dimensional world. Forward, backward, left, right, up, down. That's it. It feels obvious. But is it truly? Or is our sense of space simply limited by the structure of our minds? To probe that question, consider a book that's over a century old, Flatland by Edwin Abbott. It's a story about a world of only two dimensions. No up or down, just length and width. In Flatland, its inhabitants are geometric shapes, triangles, squares, circles, sliding along a flat plane. Now imagine a three-dimensional creature, someone like you, passing a finger through Flatland. To a Flatlander, this would be inexplicable. At first, they'd see a single point appear from nowhere. Then it would expand into a line. Then it would vanish. To them, this isn't a finger, it's a miracle, violating every known law. But to us, it's just geometry. And here's the unsettling part. What if we are the Flatlanders? What if our perception of space is as provincial, as blinkered, as theirs? Just because we're used to three dimensions doesn't mean that's all there is. Our brains evolved to build huts and hunt prey, not to intuit curved manifolds or 11-dimensional brain worlds. Just as ants on a sheet of paper can never imagine a third dimension, we too might be blind to what surrounds us. So the question becomes, what happens when physics begins to explore these higher dimensional spaces? Can we go beyond the limits of our own flatland? As it turns out, we already have. By the early 20th century, physicists were starting to realize that Newton's comforting model of space and time, absolute, steady, universal, was cracking. Albert Einstein showed that time could stretch, space could contract, and simultaneity itself could dissolve. What seemed like two separate realities, space and time, were actually fused into one. And here, again, came geometry to the rescue. A mathematician named Hermann Minkowski, who had once been Einstein's professor, gave this new unified framework a name, spacetime. And he didn't just describe it, he drew it. He treated time as a fourth dimension and showed how the bizarre effects of relativity clocks slowing down, lengths contracting, were not paradoxes or illusions. They were simply the shadows cast by movement through this four-dimensional arena. Suddenly, the mysteries of motion, the stretching of time, and the warping of rulers were no longer mysterious. They were geometric facts, and the arena itself, space-time, was now the canvas upon which all physics would be painted. Let that settle in for a moment. What began as a philosophical question about parallel lines has now led us to a radical idea that space and time are not separate things, but aspects of a single, bendable, stretchable entity. And we, every day, are moving through it, not just through space, but also through time. As we continue this journey, we'll ask even deeper questions. What happens when this space-time gets curved by mass and energy? What if that curvature is gravity? And what if that very fabric can ripple, twist, or even leak into higher dimensions? All of that awaits. But remember where it started, with a simple doubt, a question that cracked the foundation, a refusal to believe that our intuition is the final word. The moment you realize that geometry is negotiable, everything else begins to unfold. Picture a young Albert Einstein, not yet a global icon, sitting at a desk in the Swiss patent office. He's reviewing blueprints and diagrams of synchronized clocks devices designed to keep perfect time across vast distances. But something begins to gnaw at him. What is time, really? What if synchronization isn't universal? What if it depends on how you're moving? This quiet question sparked a revolution. By the early 1900s, Einstein had shattered one of the oldest pillars of physics, the notion that time ticks the same for everyone, everywhere. Instead, he proposed something radical. Time is relative, not metaphorically, literally. Time itself stretches or contracts depending on how fast you move or how close you are to a massive object. But Einstein didn't stop there. If time can bend, and space can too, then maybe they aren't two separate things at all. Maybe they are one. Enter Hermann Minkowski, the mathematician who would take Einstein's raw insight and recast it into something far more profound. He introduced the idea of space-time, a unified four-dimensional continuum where space and time are woven into a single geometric fabric. No longer were events simply here or then. They had coordinates in both space and time. A flash of lightning, a falling apple, the movement of your hand, all are points along a path through this four-dimensional space-time. And once you start thinking this way, everything starts to change. Take simultaneity, for example. Before, it seemed simple. Two events happen at the same time, or they don't. But now, whether two things are simultaneous depends on how you're moving. What's now for you might be past or future for someone speeding by. There is no universal now. That's not philosophy. That's physics. And what about distances? In a moving frame, rulers shrink. Literally, a meter stick flying past you appears shorter than one at rest. Not because of some illusion, but because of how space-time warps when you move through it. This sounds absurd, but it's been tested over and over again. Particle accelerators send subatomic particles racing near the speed of light. Their clocks slow down, their lives stretch. They live longer not metaphorically, but measurably because time is running differently for them than for us. Your GPS system works because satellites orbiting Earth experience time at a different rate than clocks on the surface. Without adjusting for relativity, your phone would be wrong by miles every single day. In other words, this isn't sci-fi. This is the world. But the deeper magic is still to come. Because once you accept space-time as a real, tangible arena, something you move through, not just exist within, you begin to see a hidden logic behind the forces we once took for granted. And the most profound of those is gravity. We all grow up thinking of gravity as a pull, a force that drags things down. Newton imagined it as an invisible string between objects. Earth pulls on you, the sun pulls on Earth, and so on. But that idea never quite explained everything. If the sun were to vanish, Newton's model says we'd feel the absence instantly. That violates another cornerstone of physics. Nothing, not even gravity, can travel faster than light. So, how do you fix that? Einstein's answer was shocking in its elegance. Gravity is not a force, it's geometry. Objects like the sun bend the space-time around them. Planets don't orbit because they're being pulled, they orbit because they're following the straightest possible path through curved space. Like marbles rolling along the curves of a funnel, or airplanes circling Earth because of its roundness, not because Earth reaches out and grabs them. In this picture, mass tells space-time how to curve, and curved space-time tells matter how to move. It's not a metaphor, it's math. And suddenly, all those bizarre observations, light bending around stars, time ticking slower near black holes, become simple consequences of geometry. The universe is not a stage on which physics plays out. The stage is physics. That realization was more than beautiful. It was predictive. In 1916, Einstein used his new theory, general relativity, to predict that light from distant stars would bend as it passed near the sunday. A few years later, during a total solar eclipse, astronomers watched that very thing happen. It was one of the most spectacular confirmations in the history of science. But this is where things get even stranger. If gravity is just the warping of space-time, then the shape of space, its curves, its folds, its unseen dimensions might explain not just motion, but everything. Maybe the deepest truths of reality aren't about particles, or forces, or energies, but about geometry. Maybe the universe is, at its core, a shape, and that idea opens the door to places far beyond our intuition. Because here's the question no one can stop asking once they've accepted four-dimensional spacetime. What comes next? If time can be treated as a dimension just like length, then why stop at 4? Why not 5? Or 10? Or 26? Is 4 truly the final frontier? Or is it just the shallow end of a much deeper pool? This is where our journey begins to diverge from experience. Because while we can move easily in 3 dimensions and reason about time as a fourth, higher dimensions, those beyond 4, don't fit into our minds so easily. We can't see them. We can't build them with blocks, but we can describe them, we can model them, and we can ask, what would it mean to live in a universe with more than 4 dimensions? What would happen to the laws of physics? To gravity? To the structure of atoms and the behavior of light? And perhaps most importantly, could such a universe be our own? As we step into the next part of this journey, we'll explore what happens when physicists dare to imagine spaces beyond the visible. We'll meet Kaluza and Klein, 2 thinkers who proposed an extra dimension not as fantasy, but as a way to unify the forces of nature. We'll learn how adding 1 extra coordinate, just 1, might unlock electromagnetism itself. And from there, the landscape will begin to warp beyond anything our Flatlander ancestors could have dreamed. But first, take a moment, breathe, let this idea settle. You are not just moving through space. You are surfing the curves of a 4-dimensional structure that bends and twists under your feet and above your head every second of your life. Reality has shape, and you're riding it. If time can be folded into space to form a 4-dimensional world, then what's to stop us from adding just 1 more? That question, once whispered in the margins of theoretical notebooks, exploded into the center of physics in the early 20th century. It began with a quiet idea. What if you could unify gravity and electromagnetism, 2 of nature's fundamental forces, not by inventing a new particle or equation, but by adding a dimension? That's what Theodore Kaluza proposed in the early 1920s. He imagined a 5th coordinate, a new axis beyond the familiar 4. But this wasn't just a wild guess. He noticed something strange and beautiful. When you take general relativity, the theory that describes gravity, and extend it into 5 dimensions, something emerges. Electromagnetism falls out of the math, as if it had been hiding in that extra dimension all along. The equations didn't just describe curvature and gravity, they also contained Maxwell's equations, the same ones that govern electric fields, magnetic fields, and the behavior of light. It was breathtaking. But there was a problem. If this fifth dimension were real, why didn't we see it? Why couldn't we move through it like we move through left and right? Enter Oscar Klein. He suggested that maybe we don't see it because it's tightly curled up. Picture a garden hose. From far away, it looks like a one-dimensional line. But get closer, and you see its circular thickness. Klein proposed that the fifth dimension is just like that, rolled up into an infinitesimal circle, so small that we don't notice it. To us, the universe feels four-dimensional, but underneath that perception, there may be extra layers, compactified dimensions hidden from view. And if one extra dimension could give rise to electromagnetism, what might more dimensions reveal? This is where the idea of hidden dimensions took root, not as fantasy, but as a new kind of geometry, one that might unlock deeper truths about the universe. It's worth pausing here, because this marks a shift in tone. Before this moment, higher dimensions were the stuff of metaphor and abstraction. But now, physicists had a reason to believe in them, a purpose. They weren't just stretching space for fun, they were solving problems. Still, the idea of extra dimensions sat quietly on the sidelines for decades. Quantum mechanics had exploded into the spotlight, dominating the attention of physicists through the mid-century. But in the background, the seed had been planted. Perhaps more than four dimensions are needed to make sense of everything. Then came string theory. In the 1970s and 80s, a new framework began to emerge, one that didn't treat particles as tiny points, but as one-dimensional strings vibrating in a higher dimensional space. These strings weren't metaphors, they were physical entities, mathematically precise, with specific vibration patterns corresponding to all known particles. And here's where things get strange. String theory doesn't just prefer extra dimensions, it requires them. The math demands it. In the most consistent versions, space-time must have not four, not five, but 10 dimensions, 9 of space, 1 of time. Later variations, like M theory, push that number to 11. These extra dimensions aren't optional, they are built into the structure of the theory itself. Without them, the equations break down. Internal inconsistencies, called anomalies, appear and ruin everything. It's as if the universe has been whispering, I am not what I seem, I am larger, deeper, folded. But again, the question returns, where are these dimensions? Why don't we move through them? Just as Klein suggested for the fifth dimension, string theorists believe that the extra dimensions are compactified, curled up in intricate shapes, far smaller than anything we can currently probe. These aren't simple circles. They are rich, complex manifolds with strange topologies, Calabi-Yau spaces, folded in on themselves in ways we can barely visualize. And yet, these shapes matter, because the exact geometry of these curled-up dimensions determines how strings vibrate, and how strings vibrate determines everything: mass, charge, spin, interaction strength. The very identity of particles depends on the shape of space itself. Let that sink in. The fabric of reality, the very nature of matter, may depend on the geometry of hidden dimensions. It's a stunning idea that we are not just shaped by the laws of physics, but that those laws arise from the shape of unseen space. We are the music of extra dimensions. Still, skepticism remains. No one has yet seen an extra dimension. We can't point a telescope at it. We can't tunnel into it. For now, it exists in the realm of theory, beautiful, consistent, mathematically elegant, but unproven. But here's why it matters. Physics needs this. Our best theories, the standard model of particle physics, and general relativity work beautifully in their own domains, but they refuse to merge. The moment you try to quantize gravity, things fall apart. Equations explode into infinities. Predictions stop making sense. But in string theory, everything stays smooth. Gravity becomes quantum, and particles become geometry. Extra dimensions aren't a bug, they're the reason it works. So we're left with a question. Do we live in a universe with more dimensions than we can perceive? Are we shadows on a higher dimensional stage? Flatlanders, still, but now walking not on paper, but on the walls of an 11-dimensional cathedral? And if we are, can we ever climb those walls? In the next part of our journey, we'll explore what happens when these extra dimensions aren't just curled up, but vast, when we imagine that we are not moving through space, but stuck on something. A membrane, a brain, floating in a higher dimensional world called the bulk. We'll dive into brain world models, learn how gravity might leak into other dimensions, and how the very weakness of gravity might be a clue to the existence of parallel brains neighboring universes just out of reach. And we'll ask, could we ever touch them? But for now, hold this picture in your mind. The universe may not be a flat sheet or a box or even a sphere. It may be something far more subtle, a folded, vibrating, multidimensional tapestry, and you are a part of its song. You've been told that space is vast, that the universe is expanding in all directions, galaxies drifting apart like islands on a dark ocean. But what if that ocean has a shoreline? Or better yet, what if we're floating on it? This is the strange and beautiful idea of the brain world. In string theory, particles are not zero-dimensional points, but tiny vibrating loops. And in some versions of this theory, particularly the branch known as M theory, those strings aren't the only fundamental structures. There are also higher dimensional objects called brains, short for membranes. A brain can have one dimension, like a string, or two, or three, or more. And according to these models, our entire universe might be a three-dimensional brain suspended inside a larger, higher dimensional space called the bulk. That's right. Everything we know, every atom, every star, every memory and moment could be confined to the surface of a cosmic membrane. We might not be drifting in the universe. We might be stuck to a floating sheet, like dew on a spiderweb. And it gets even weirder, because while the matter and light we're familiar with, electrons, photons, everything described by the standard model of physics might be confined to this brain, gravity may not be. It could be that gravity leaks. Here's the idea. In our everyday world, gravity is incredibly weak. You can test this yourself. A tiny fridge magnet can lift a paperclip against the pull of the entire Earth. Gravity is, somehow, 10,000 billion times weaker than electromagnetism. Why? Some physicists think it's because gravity is spread out. While the other forces are stuck to the brain, gravity may extend into the bulk, diluted across extra dimensions. Like a flashlight beam diffusing through fog, its strength becomes faint the further it spreads. We only feel a whisper of it. If true, this would explain one of the biggest mysteries in physics: why gravity is so weak compared to everything else. Not because it's inherently puny, but because most of its power is hiding in dimensions we can't touch. But there's more. If gravity can travel into the bulk, then maybe it can touch other brains. This opens the door to a wild possibility. Parallel universes, not in some distant region of space, but right next to us, hovering in a dimension we can't enter. Entire worlds, governed by the same physics, existing a microscopic distance away, separated not by miles but by geometry. We wouldn't see these parallel brains. Light can't travel between them, but gravity might. And if it does, we might someday detect its pull, small deviations from Newton's inverse square law, slight anomalies in experiments with ultra-sensitive detectors. These are not pipe dreams. Physicists have already performed such experiments, trying to measure gravitational force at millimeter scales, searching for signs of extra-dimensional leakage. So far, nothing has turned up, but the precision is improving. And here's where things become mythic. Some versions of brain world cosmology suggest that the Big Bang itself might have been a collision between brains. Picture two giant membranes floating in the bulk. Over eons, they drift and then impact. A cosmic tremor that floods each brain with energy, birthing matter, time, and space as we know it. We wouldn't see the other brain. We'd just see the aftermath, an expanding universe, glowing and cooling, filled with stars and galaxies. In this view, the birth of our universe wasn't the creation of everything. It was an event in a larger arena, one of many. And just like tectonic plates on Earth can crash and reshape continents, brains in the bulk might collide again. Future universes, recurring cycles, cosmic rhythms, pulsing through dimensions we barely understand. It's not science fiction. It's math. The equations of string theory and M theory support these ideas. They don't require them, but they allow them. They whisper of deeper structures, hidden architectures of space that might explain the weirdness we see, the fine-tuning of constants, the weakness of gravity, the early inflation of the cosmos. And more than that, they suggest a testable framework, deviations in gravity, cosmic microwave background patterns, high-energy particle collisions that might, for an instant, reveal the influence of higher dimensions. This isn't fantasy, it's a search. But here's the part that hits hardest. If brains are real, and we are stuck on one, then our universe is just a slice of something larger, a shadow on a cosmic wall, a ripple in a multidimensional sea. And that challenges something deep within us. We like to believe we are central, that the universe, for all its vastness, is somehow ours, that it begins and ends with us. But brain theory says otherwise. It says we may be one of many, a single membrane in a frothing foam of realities, and we may never cross the gap, never glimpse what lies on the next brain, never hear the music of its particles or see the light of its stars. Or maybe, just maybe, we already do. Maybe dark matter, the mysterious, invisible substance that outweighs normal matter, 5 to 1 isn't stuff at all. Maybe it's gravity leaking in from another brain, a shadow, not of our universe, but of a neighbor's. This is a bold claim. It's speculative, but it is not baseless. In the next chapter, we'll explore an even more dramatic theory, one that explains not just the shape of the universe, but its origin story. We'll dive into the idea of cosmic inflation, an astonishing burst of expansion that occurred in the first sliver of a second after the Big Bang. We'll see how this theory, simple and elegant, not only solved several cosmic puzzles, but led, almost accidentally, to the notion of an eternal inflation, a process that creates not just a universe, but an infinite fractal multiverse, a never-ending bloom of pocket worlds. And once you let that in, once you see how inflation gives rise to endless diversity, you'll start to feel a strange sensation that your universe might just be one petal on a flower of unimaginable complexity. But that's for next time. For now, sit with this image. You are floating not in empty space, but on a brain, a vast, invisible surface embedded in a higher dimensional world. Your feet don't rest on solid ground, they rest on geometry. And beyond that geometry might be another world, just out of reach. Try to imagine the entire visible universe, 100 billion galaxies, each with hundreds of billions of stars. Now, try to picture it inflating, doubling in size, then doubling again. Not over billions of years, but in a tiny sliver of time. Less than a trillionth of a second. This is not a fantasy. It's called cosmic inflation. In the early 1980s, physicist Alan Guth proposed a radical idea. He was trying to solve a cosmic mystery. Why is the universe so uniform? No matter which direction you look, the temperature of the cosmic microwave background, the oldest light in the universe, is nearly identical. Too identical. According to the standard Big Bang model, there hadn't been enough time for light to travel between distant regions to even out those temperatures. The solution Guth proposed was inflation. He suggested that in the earliest moments after the Big Bang, the universe underwent an extraordinary expansion. Space itself didn't just grow, it exploded faster than the speed of light. Not in violation of relativity, but because relativity limits the speed of objects within space, not space itself. During this inflationary period, which lasted a fraction of a second, any wrinkles, warps, or temperature differences were stretched flat like imperfections in a balloon disappearing as it inflates. Inflation smoothed out the universe, explained the uniformity, and made sense of the enormous size we now see. But inflation came with side effects. It predicted that space would be flat, overall. and that the universe should contain tiny, quantum-sized fluctuations, minuscule energy variations that would be stretched across the cosmos. These would later seed the galaxies, the stars, the structure of everything. And when scientists looked at the data from satellites like COBE and WMAP, they found precisely these fingerprints. The map of the early universe, the small variations in the cosmic microwave background matched what inflation predicted. It worked. But here's where things turn from astonishing to surreal. Because inflation isn't just a one-time event. In many models, once inflation starts, it never truly stops. It ends in pockets, small regions where the inflationary energy decays, space cools, and particles emerge. That's where universes like ours are born. But in other regions, inflation continues. Space keeps doubling. The energy keeps expanding. It's a cosmic fractal, endlessly budding. This idea is called eternal inflation. In this framework, the Big Bang wasn't a singular beginning. It was a local event, a bubble, one of countless others. Our universe, our entire observable cosmos, is just a pocket within a much larger inflationary field. Beyond our horizon, beyond what we can ever see, other bubbles are forming. Universes, each born in their own Big Bang, each with their own constants, laws, maybe even dimensions. It's a multiverse, not by speculation, but by consequence. Inflation doesn't just allow it, it almost requires it. Let that sit for a moment. The vastness you've imagined, your whole life, trillions of galaxies, might be nothing more than a speck in a much grander system. A cosmic foam, with bubbles constantly blooming, each a universe, each unknowable to the others. And these bubbles are not all the same. Some may have more matter, some may expand faster, others may never form galaxies. Still others may collapse back into themselves seconds after forming. In some, stars may never shine. In others, the laws of physics may twist into forms we can't even imagine. Why does our universe allow life? Why does it have stars, chemistry, stable atoms? Because we live in one of the rare bubbles where all of it works. This is the core of what's sometimes called the anthropic principle. Not that the universe was designed for us, but that we could only ever find ourselves in a universe where observers can exist. It's not an answer that satisfies everyone. Some physicists find it uncomfortable, even unscientific. But in the context of eternal inflation, it becomes less a philosophical cop-out and more a statistical inevitability. And yet, there's something eerie here. Because eternal inflation creates not just many universes, but infinite copies. Given enough time and enough space, everything that can happen will happen not once, but endlessly. There is, out there, a version of you reading these words, but wearing a different shirt. Another where you didn't finish this sentence. Another where Earth never formed. Another where it did, but life never emerged. It's dizzying. Some call this the Level 1 multiverse, an infinite universe beyond our observable bubble, where duplicates exist simply because space goes on forever. The Level 2 multiverse goes further, not just duplicate arrangements of matter, but different laws altogether, because each inflationary bubble has its own initial conditions, its own physics. These aren't parallel timelines. These are separate cosmic regions, forever disconnected by the expansion of space itself. We will never see them, never touch them, but their existence may be written into the fabric of our universe in the distribution of matter, the flatness of space, the faint hiss of ancient light. And this is where we must pause. Because while the inflationary multiverse solves problems, it makes testable predictions, it explains observations, it also leads to a haunting realization. If the multiverse is infinite, how do we make predictions at all? This is the measure problem. When everything happens infinitely often, how do you assign probabilities? If there are infinite universes with galaxies and infinite without, how do you say what's likely? What does science even mean in such a landscape? This is not a fringe concern. It's one of the deepest unsolved questions in cosmology. Some physicists argue we need a new kind of probability. Others say we may need to redefine what it means to explain something. Still others say the multiverse itself is untestable and therefore unscientific. But here's the twist. If inflation is true and it matches our data astonishingly well, then the multiverse might not be optional. It might be the price we pay for understanding why anything exists at all. And the implications are profound. It means that our universe is not the story. It's a chapter, a stanza in an eternal poem, a single splash in a sea of cosmic possibility. And still, we must ask, is this the end of the road, the final horizon? Or is there another layer, deeper still? Because there is yet another multiverse. One not born from inflation or bubbles, but from the quantum structure of reality itself. A multiverse, not of space, but of possibilities. In the next part of our journey, we'll descend into the many worlds interpretation of quantum mechanics. We'll see how every quantum decision, the path of a photon, the spin of an electron may split the universe into branches, and how all of them might still exist, side by side, forever. But before we go there, reflect on this. The universe, stars, galaxies, gravity, time is just one breath in an infinite bloom, and beyond it, more blooms, and beyond that, a silence filled with possibility. You've heard of the multiverse born from inflation, an eternal bloom of pocket universes. But there is another kind of multiverse, one that doesn't grow in space, but in possibility. It doesn't arise from the geometry of the cosmos, or the explosion of baby universes in the early seconds of time. It emerges from the most fundamental level of physics, the quantum realm. Welcome to the many worlds interpretation. To understand it, we must enter the strange terrain of quantum mechanics, a place where particles can be in two states at once, where electrons don't orbit like planets, but exist in clouds of probabilities, where observation itself seems to play a role in determining reality. The classic example is the double-slit experiment. Fire a stream of particles, say, photons or electrons, at a screen with two open slits. If you don't observe which slit each particle passes through, you'll get an interference pattern, light and dark bands, as if each particle went through both slits and interfered with itself. But if you measure which slit it went through, the interference vanishes. The particle chooses a path, and the wave-like behavior disappears. It's as if the act of measurement collapses the wave of possibilities into one outcome. But that's just one way to interpret it. In the many worlds interpretation, the wave function never collapses. Instead, every possible outcome happens each in its own branch of reality. When you observe the particle, you don't force it into one path. You simply split. There is now one version of you who saw it go through the left slit, and another who saw it go through the right. The universe forks, again and again. This isn't poetic metaphor. It's a literal reading of the mathematics. The equations don't need collapse. They evolve smoothly and deterministically. It's we who experience a split, because we are part of the system. Every time a quantum decision occurs, when a radioactive atom decays or doesn't, when a particle spins up or down, when a photon reflects or passes through reality branches. And these branches aren't illusions. They're as real as the one you're in right now. That's the proposal. You are living in a universe that is constantly dividing, fracturing into an ever-growing tree of outcomes. A quantum garden where each branch is a world, and every possibility is realized somewhere. In this view, the multiverse doesn't lie out beyond the stars. It lies beneath your feet, beneath your thoughts. Every decision you've made or didn't make has a version that plays out in another world. There's a version of you that chose a different path, a version that turned left instead of right, a version that didn't watch this video, a version that isn't here at all. It's tempting to imagine these versions as accessible, as if you could step into another branch, shake hands with another self. But the truth is stranger. The branches are causally isolated. Once they diverge, they no longer interact. They are decoherent, meaning that no signal, no information, no photon can pass between them. They are out of contact, forever. So why propose this at all? Because the many worlds interpretation does something profound. It takes the weirdness of quantum mechanics and removes the mystery. It says, don't try to make the universe classical again. Accept that reality is fundamentally quantum. Accept that the wave function is real. Accept that the world is bigger than your perception of it. In doing so, you gain simplicity. No special rules for measurement, no wave function collapse, just a clean, mathematical unfolding of the universe. Of course, it raises its own questions. If all outcomes occur, why do we only experience one? Why do probabilities still make sense? Why is one outcome more likely than another? These are serious concerns, and physicists continue to debate them. But many worlds remains one of the most compelling ways to interpret quantum physics without adding extra ingredients. And there's more. Remember those higher dimensions we discussed earlier? The ones from string theory? Here's where things get surreal. Some physicists suggest that the wave function, the mathematical object that holds all quantum possibilities, doesn't live in ordinary space at all. It lives in a vast, abstract configuration space. In this space, every possible arrangement of every particle in the universe is a point. It's not 3 dimensions. It's not even 10. It's a space of unimaginable dimensionality. Each degree of freedom gets its own axis. For a system with 100 particles, that's hundreds of dimensions. And in this mind-bending space, the wave function evolves smoothly. No collapse, just flow. And decoherence caused by entanglement with the environment splits the wave function into non-interacting sectors. These sectors are your parallel worlds. So in a way, the multiverse of many worlds isn't about branching space, it's about structure, about how reality navigates a labyrinth of possibilities, each one encoded in the wave function's trajectory through a vast configuration space. It's abstract, it's hard to visualize, but it's precise. And it may be real, because quantum mechanics is not optional. It's been tested to absurd precision. It works. And if its cleanest interpretation is that reality constantly forks, then perhaps we must learn to live in a universe where everything possible is real somewhere. Still, it's hard not to feel a kind of loss. In this vision, you are not a unique story. You are one of many. Every outcome is realized, every path taken, every tragedy and triumph echoed elsewhere. But there is beauty in that too, because your consciousness, the you that's here, now is riding a unique branch through an infinite forest. You're not less meaningful, you're more. You're part of a vast superstructure of experience, stitched together by the laws of physics into something far grander than any one outcome. And the journey doesn't end here, because there is one final step, a place where all these threads converge. What happens when we combine the geometry of relativity, the dimensions of string theory, and the probabilities of quantum mechanics? We reach the edge of our understanding, the quest for quantum gravity, a theory that unites all forces, all dimensions, all realities into one coherent whole. And in that search, we encounter even more exotic ideas: black hole information, holographic principles, emergent space-time, and the wildest notion of all that reality itself might not be fundamental, but emergent, a kind of computation, or pattern, or code. We'll explore that in the final chapters. But for now, reflect on this. You are not a single path. You are a strand in a cosmic braid, woven from possibility itself. Every moment, every quantum whisper, carves a new world into being. And the garden keeps growing. We've walked through infinite bubbles of space. We've wandered the branching forest of quantum decisions. And now, we arrive at a precipice, the place where all our ideas about reality begin to collide. Because if the universe splits with every quantum choice, and if inflation endlessly spawns new cosmic bubbles, and if extra dimensions bend gravity into places we'll never reach, then the question becomes, what exactly is real? It's not just a poetic question, it's a physics problem. When physicists try to tie together quantum mechanics, general relativity, and cosmology, they run into a wall, a deep, unresolved conflict between the smooth geometry of spacetime and the probabilistic chaos of quantum fields. These two theories are stunningly successful on their own. They've passed every test we've thrown at them, but when you try to unify them, especially at the smallest scales, near black holes or the Big Bang, everything breaks. So what if reality isn't what we think it is? What if all the things we thought were basic space, time, particles are just approximations, illusions that emerge from something deeper. That's the new frontier. And at the heart of that frontier is a word you may not expect: information. This shift began with a paradox. In the 1970s, Stephen Hawking discovered that black holes aren't perfectly black. They radiate a faint quantum glow, now called Hawking radiation. Over time, a black hole loses mass, shrinks, and eventually disappears. But if that's true, it creates a crisis, because quantum mechanics tells us that information is never lost. Every process is reversible. If you know the final state of a system, you should be able to trace it back to the beginning. But black holes seem to erase information. They swallow whatever falls in books, atoms, entire stars, and then vanish, leaving behind only a bland thermal residue. So, where did the information go? This is known as the black hole information paradox, and it shook physics to its core. Some argued that information really is lost, violating quantum law. Others said the information must somehow be encoded in the Hawking radiation, hidden in delicate correlations we don't yet understand. But one idea rose above the rest, and it changed everything. It's called the holographic principle. It proposes that all the information in a volume of space, every particle, every event, every memory, is actually encoded not in the volume, but on its boundary. Like a hologram, where a two-dimensional surface contains all the information needed to reconstruct a three-dimensional image, the universe itself might be a projection. Let that sink in. Everything you've ever seen may be a shadow of data written on the edge of space. This isn't philosophy. It comes from hard math, from studies of black holes and string theory. It suggests that the true laws of nature might not be about fields in space, but patterns on surfaces. We don't yet know what these surfaces are in our universe. But in certain simplified models, like a type of space called anti-de Sitter space, the math works perfectly. Physics inside the volume corresponds exactly to quantum theory on the boundary. This duality has a name: ADS, CFT correspondence. It's been called the most important development in theoretical physics since quantum field theory itself, and it hints at something profound. That gravity, the warping of space-time, is not fundamental. It emerges from quantum entanglement. That space itself may be woven from information links between particles. You are not simply moving through space. You are a part of its architecture. This is the dream of a quantum theory of gravity, a framework that unites the two great pillars of modern physics into one coherent whole. And in this dream, multiverses aren't speculation. Their structure: you have the multiverse of inflation, the eternal cosmic bloom. You have the multiverse of quantum mechanics, the infinite branching of outcomes. You have the multiverse of string theory, where the shape of extra dimensions determines the laws of physics in each universe. And now, you have a multiverse of holographic boundaries, where each surface can encode an entire cosmos. These aren't layers of fiction, they're layers of description, each a different way of slicing the same impossible object, reality. But what is reality? If you strip away particles, waves, space, and time, what remains? Many physicists now believe the answer lies in information, not bits in a computer, but the fundamental relational data that defines everything: how one thing affects another, how entanglement links the fates of distant particles, how the curvature of space tells matter how to move. In this view, the universe is not a thing, but a pattern, a computation, a story told by interacting pieces of information, constrained by logic, yet endlessly expressive. Which brings us to a final, mind-bending idea. Perhaps consciousness, your sense of being, your flow through time, is not outside of this pattern, but part of it. Perhaps your thoughts are quantum events, branching worlds. Perhaps your choices shape the path your universe takes, not by force, but by entanglement. And perhaps, just perhaps, the reason this universe allows life, allows memory, allows you, is because information wants to observe itself. The universe dreams, and you are the dreamer and the dream. We are approaching the edges now. Beyond this lies the speculative, the unsolved, the poetic frontier, where physics meets philosophy. In the final chapters, we'll step into this unknown, into the theories that attempt to unify everything, from string landscapes to loop quantum gravity, from emergent spacetime to the idea that our cosmos might be a simulation running on a substrate we cannot comprehend. But before we leap off that cliff, let's take a moment. Close your eyes. Feel the breath of time, the weight of space beneath you, the entanglement of your atoms with the stars. You are not separate from the cosmos. You are its pattern, folded into its song, and the multiverse may be humming through you. We've reached the edge, not just the edge of space or time, or even of what science can measure, but the edge of our definitions. Because now we must ask a question so radical, so destabilizing, that even many physicists whisper it with hesitation. What if space-time isn't real, not unreal like a dream, but not fundamental either, not the thing from which everything else arises, but something that emerges, like temperature emerges from molecules, or a rainbow emerges from the bending of light? This is the strange idea now sweeping through theoretical physics, that space, time, and maybe even reality itself are not basic. They're constructed not by us, but by something deeper. Let's unpack that. In quantum mechanics, particles can be entangled, so deeply linked, that knowing something about one instantly tells you something about the other, no matter how far apart they are. This isn't magic. It's a natural, measurable feature of the quantum world. But what's strange is that entanglement doesn't care about distance. Two entangled particles can be on opposite sides of the galaxy, and the correlation remains. It's as if their connection exists outside of space. And here's where things start to turn. Some physicists began to wonder, could it be that entanglement is more fundamental than space itself? That the very fabric of space emerges from quantum entanglement? This idea, once fringe, is now finding mathematical traction in models of holography, where a lower dimensional quantum system can encode a higher dimensional gravitational world. The amount of entanglement between parts of the boundary seems to correspond to the geometry of the interior, space. More entanglement equals space is connected. Less entanglement equals space begins to break apart. So think about that. You're used to imagining space as the fixed stage on which matter moves. But in this view, space is a consequence of relationships, a map of entanglement. The distance between things isn't a pre-existing grid, it's a reflection of how correlated those things are quantum mechanically. And time? Time, too, may be emergent. Some theories suggest that time arises from a change in entanglement, that what we call now is just a slice through a flow of relational information. A page in a book whose ink is quantum connectivity. These are not metaphors. Mathematicians are now trying to reconstruct Einstein's equations of gravity, the ones that describe curved spacetime from purely entropic principles. That is, from the rules of information flow, not from any assumption about geometry. Gravity, in this picture, is not a force. It's not even curvature. It's a thermodynamic response to changes in information. You've seen this kind of thing before. Heat isn't a substance. It's the result of many particles jostling around. Pressure isn't a thing. It's what happens when all those molecules hit a wall. Temperature, volume, entropy, their emergent properties. What if spacetime is like that? What if everything we perceive, the solidity of the ground, the ticking of a clock, the feel of motion, is like weather, arising from patterns far beneath our awareness? This is the heart of emergent spacetime. And if that's true, it might explain some of the deepest puzzles in physics. Why gravity is so weak, why black holes behave like thermodynamic objects, why quantum mechanics refuses to fit neatly into classical frameworks. Because we've been trying to quantize gravity as if it were a fundamental force. But if gravity is emergent, that's like trying to quantize sound by studying individual air molecules. You can do it, but it misses the point. The key might lie beneath gravity, beneath space, beneath time, in a code. Some physicists believe that what we experience as physical law is the result of a computational process. not metaphorical computation, but something real. That the universe is made not of atoms or strings, but of bits, units of information that update, entangle, and evolve, not in space, but into space. It's a radical idea, but it matches something deep in how our theories behave. In many models, space-time behaves like a network, nodes connected by links. The links are not distances, but relations, ways in which quantum systems influence each other. Space appears when the network becomes dense and regular enough. Time appears when the patterns evolve. This is the world according to quantum gravity, tensor networks, loop quantum gravity, and other speculative frameworks that try to go deeper than the theories we've mastered. And you might ask, where's the evidence? Well, one hint lies in the black hole firewall paradox, a conflict between quantum mechanics, relativity, and the smoothness of space-time at the event horizon. To preserve quantum information, black holes may have to violate the very idea of a smooth geometry at the edge, suggesting that space-time itself breaks down at extreme conditions. That beneath the horizon lies something else, not a place, but a state of information. Another clue lies in the ADS CFT correspondence, which shows that a purely quantum system on the boundary of a space can reproduce all the physics inside that space, gravity included. In these models, you don't need to build space-time. It emerges naturally from the quantum structure on the boundary, like a soap bubble forming from the interaction of molecules. But if all of this is true, if we are living in an emergent geometry built from something deeper, we must face a chilling question. What is the substrate? What is this something deeper that gives rise to everything? Is it an actual computation? A vast, universal quantum state? Is our universe running on something? Is there a cosmic hardware beneath our software? This leads some thinkers, serious thinkers, to consider the possibility that we are inside a simulation, not a digital cartoon, but a structure running on principles we do not yet understand. A generative system, producing universes from rules, as a game engine produces worlds from code. This doesn't mean you're fake. It doesn't mean you're not conscious. It means that reality is a process, and processes run on something. It could be that the very laws we hold sacred, relativity, quantum mechanics, thermodynamics, are simply effective rules, true at our scale, but not at the base, like the laws of traffic in a city not built into the asphalt, but emerging from deeper social coordination. This doesn't destroy meaning, it makes meaning bigger, because if the universe is emergent, then meaning, beauty, wonder, these are not decorations on top of reality. They are part of its unfolding. You are not moving through space-time. You are a ripple in the structure that makes space-time possible. You are not living inside the universe. You are the universe, organizing itself into experience. And now, as we approach our final chapters, we'll look at what this means for consciousness, for the self, and for the limits of what physics can ever truly explain. Because beyond the multiverse, beyond geometry, beyond code, there may lie a different question entirely. Why is there awareness at all? We've followed the curves of space-time. We've watched dimensions fold into hidden shapes. We've wandered the forests of many worlds, peered into the black hole's secret, and stepped onto brains, suspended in a higher dimensional bulk. But now we must face something even more intimate, something stranger than quantum fields and deeper than geometry. Consciousness. It's the only thing you're absolutely sure of. Before you can be certain there's a world, you are certain there's an experience, a presence, a point of view, a witness. Physics can describe the motion of galaxies, the trembling of electrons, the birth and death of stars. But when it tries to describe you, something shifts. Not your body, not your brain, not even your neural networks, but you, the subjective eye behind the eyes. What is that? Where does it come from? Is it just a trick of biology, neurons firing in patterns so complex they hallucinate a self? Is consciousness an emergent property, like temperature, appearing when enough parts come together? Or is it something deeper? In recent decades, a growing number of physicists and philosophers have asked a radical question. What if consciousness is not a byproduct of the universe, but a fundamental feature of it? This is not spiritual woo. It's a serious shift in perspective, driven by the recognition that awareness doesn't sit comfortably inside our current theories. Take the hard problem of consciousness. We can measure brain activity. We can scan patterns of electrical pulses and chemical exchanges. We can correlate neural firing with decision-making and language and emotion. But none of that explains why it feels like something to be you. Why red looks red. Why a song can make you cry. Why love or sorrow or all subjective experiences exist at all. Physics, in its current form, is about structure and prediction. It tells us how things behave, but it doesn't account for what it's like to be something. And yet, your entire reality is built on that what its likeness. This has led some thinkers to propose that experience qualia isn't emergent, it's elemental, that perhaps every particle, every system, has some primitive form of experience, not thoughts, not memory, but some seed of subjectivity. This is the idea behind panpsychism, the view that consciousness is not something that happens to matter, but something that pervades it. That just as mass and charge are intrinsic properties, so too might be awareness, in some minimal form. It's unsettling, yes, but consider this. If space-time can emerge from entanglement, if gravity can emerge from entropy, then why not consciousness emerging from patterns of information? Or perhaps more provocatively, what if consciousness is the substrate? Some interpretations of quantum mechanics flirt with this idea. That measurement, what collapses a wave function, may be tied to observation, not mechanical interaction, but awareness. It's dangerous territory, easy to misinterpret. But even the cautious giants of physics, John von Neumann, Eugene Wigner, entertained the notion that mind and matter are not separate realms, but intertwined expressions of the same deeper reality. Some researchers now explore models where consciousness plays an active role in how the universe unfolds, where choices made by conscious agents, however small, guide the evolution of quantum branches, not by violating physics, but by weaving it. We don't have a theory of this yet. We barely have the language. But we are beginning to suspect that the story of the universe may be incomplete without the experiencer. Think about this. You can describe a wave function in a Hilbert space. You can chart the curvature of space-time. You can model entropy, complexity, emergence. But all of that happens within awareness. The equations live in minds. The measurements are read by observers. The cosmos becomes a cosmos only when it is contemplated. And maybe that's not incidental. Maybe that's not background. Maybe that's the point. Some thinkers, like integrated information theory, IIT, proponents try to quantify consciousness itself, giving it a mathematical backbone. Others, like Roger Penrose, search for links between consciousness and quantum gravity, imagining microtubules within neurons dancing with quantum coherence. All of this is speculative, but it grows from a sense that something essential is being missed, that the subjective and the objective are not enemies but reflections of a single, unified structure. Perhaps the universe is not a machine, but a mirror, and in that mirror, awareness recognizes itself. This takes us to an astonishing possibility. What if the multiverse is not just a physical garden of branching worlds, but a garden of awareness? Each universe, a unique way the cosmos experiences itself, some with matter, some without, some with minds, some silent, some, perhaps, where consciousness bloomed in forms we'll never understand. In this view, your awareness is not a fluke of chemistry. It is a mode of being in a vast possibility space. A temporary flame, yes, but one whose light matters, because it illuminates reality from the inside. You don't merely observe the universe, you complete it. So where does this leave us? We've walked through strings and brains, fields and bubbles, entropy and emergence. We've watched space-time crack open into something more abstract, more informational, and now we've reached the place where science begins to speak softly, where it leans in, whispering, "There's something here we don't understand." Not just out there, in the dark, but in here, where thoughts rise like waves and fall again into silence. In our final chapter, we'll bring all of this together. We'll explore the ultimate synthesis, theories that attempt to explain not just physics, but existence itself. The mystery of being, the possibility that the cosmos is not a brute fact, but a self-generating, self-reflecting system. One where information becomes structure, structure becomes awareness, and awareness wonders. Why? At the beginning of this journey, we asked questions about space, about time, about dimensions beyond perception, and particles beneath our skin. We asked how the universe works, what it's made of, how it grows, how it splits. But now we've reached the question that underlies them all. Why is there anything at all? Why isn't there just nothing? No fields, no quarks, no space-time foam, no numbers, no laws, not even vacuum, just the pure absence of being, the eternal silence. It's a question older than science. And it's a question science has tried to avoid not because it's unimportant, but because it's so hard to frame, let alone answer. But now, with physics reaching its deepest paradoxes, with cosmology unfolding into an infinite multiverse, and with consciousness refusing to be a passive bystander, the question returns. And it cannot be ignored. Let's start with the simplest version. Could the universe have come from nothing? In some interpretations of quantum theory, the answer is yes. Vacuum fluctuations, the spontaneous appearance of particles from an empty quantum field, suggest that nothing is unstable, that given enough time, even true emptiness can seed a universe. This is sometimes called the quantum creation model. It treats the universe like a quantum event born from a fluctuation in a larger structure, perhaps a false vacuum, that decays into our expanding cosmos. But here's the catch. That version of nothing isn't really nothing. It's a something, a pre-existing quantum field governed by laws, containing energy, obeying symmetries, a framework, a stage, a system. It's not the absence of everything. It's like pulling a rabbit out of a hat and then discovering the hat is part of an infinitely large, pre-stitched rabbit-generating machine. The deeper question is, where did that come from? Even multiverse models, elegant as they are, often assume a set of background laws. Inflation, string theory landscapes, the structure of Hilbert spaces all require some bedrock. But where did that come from? Some physicists and philosophers suggest we've been asking the question the wrong way. Instead of asking why this universe, we might ask, why these laws? Or even, why any laws? And here, one idea emerges strange, terrifying, and beautiful. The mathematical universe hypothesis. It proposes that all mathematically consistent structures exist, not just the ones we find elegant or useful or observable, all of them. Every logical system, every axiomatic framework, every self-consistent configuration of information, each is real in its own domain. In this view, our universe exists not because it was chosen, but because it can exist, because the equations hold, because the logic doesn't break. We live inside a mathematical object, a structure that happens to allow particles, chemistry, stars, minds. There are countless others that do not, but they exist too. And then the question becomes not why is there something, but rather, why are we in this particular something? Why do we find ourselves in a universe with galaxies, complexity, memory? Because in this vast landscape of possible structures, only some permit observers. Only a fraction of mathematical universes are inhabitable. Even fewer are contemplative. Fewer still give rise to something that can ask why. This is the anthropic selection principle, taken to its logical extreme. It doesn't answer the mystery, but it reframes it. We're not here because this universe is special. We're here because it's one of the few that allows here to exist at all. Still, there's something unsatisfying about that, because math is structure, and structure is still something. Laws, even abstract ones, are not the absence of being. So we circle back. Why is there logic? Why are there laws? And here we enter territory beyond physics into metaphysics, into what some would call the realm of meaning. One possible answer is that existence is necessary, that nothing is unstable or even impossible. that the concept of nothing is incoherent, that once you have logic, you have being. Another possibility, that the universe is self-generating, that it contains the seed of its own creation, a closed causal loop where existence begets existence. A third idea, that existence is an expression, not a deduction, that the universe is not a machine, but a gesture like music or a poem, that it happens not because it has to, but because it can. In that view, the cosmos is not built, it is sung, not because of necessity, but because of beauty. And you are part of the song. One more possibility, strange yet inevitable, maybe asking why is the wrong question. Maybe why is a product of minds like ours, trained by evolution to seek causes and patterns, shaped by survival and storytelling. Maybe the ultimate question is not why anything, but what does it mean to exist at all? Or, even more humbling, what does it mean to ask? In this light, the universe becomes a mirror, not of shapes and shadows, but of questions themselves, a place where meaning is not found, but made, a canvas that paints back. As we bring this journey to a close, let's return to where we started. You, sitting in your corner of space-time, listening, wondering, thinking. The fact that you exist, that anything exists, is still the most astonishing fact there is. Physics can describe it, math can structure it, but you are the one who gives it weight. You are the light in the equation. You are the flame in the formula. You are the awareness that makes the universe aware. We began with a crack, a fracture in geometry, a whisper that the parallel lines we'd trusted since childhood might not be so parallel after all. A quiet unraveling of everything we thought was certain about space and time. And from that single crack, a flood, dimensions multiplied, gravity turned from force into shape, universes bloomed like fractal flowers, particles danced not as dots but as vibrations on invisible strings, space-time itself dissolved into information, and at the end, when even the equations went silent, consciousness remained. You've traveled far, from Euclid to Einstein, from Riemann to the quantum multiverse. You've walked the edges of physics and peered into the hollow center where the questions outnumber the answers. And now, here you are, still wondering, still awake, still here. So what have we found? We found that space is not an empty container, but a relational tapestry woven from interactions. We found that time is not an arrow, but a direction in a deeper arena where past, present, and future may all coexist. We've found that gravity is not a tug, but the bending of possibility itself. We've found that particles are not building blocks, but fleeting patterns in quantum fields, fields that may be embedded in dimensions we cannot touch. We've found that observation doesn't merely reveal reality, it participates in shaping it. And, perhaps most unsettling of all, we've found that the observer, the you who is listening to this right now, might not be a passive traveler, but part of the machinery that makes the universe unfold. Because here's the truth that humbles every physicist, mystic, and dreamer alike. We do not stand outside the universe, studying it. We are inside it, made of it, moved by it. Every thought you've had, every breath you've drawn, every aha moment where something finally made sense was space-time, reflecting on itself. You are not a spectator. You are the experiment. You are the equation. You are the unfolding. We began this journey thinking about dimensions, but dimensions weren't the point. We asked about gravity, but gravity was just the first veil. We explored the multiverse. But the multiverse was never the destination. The point was meaning. The point was to sit still in the vastness and feel its weight, to know that the same laws that shape galaxies shape your hands, to feel time not as a ticking clock, but as the soft erosion of light, to wonder not just what the universe is, but why it bothers to be at all, and in that wondering, to realize something quietly enormous. That awareness, the thing you call you, may not be an accident. Maybe it's not the final glitch in a chemical storm. Maybe it's not a side effect. Maybe it's the feature. Maybe the cosmos needed to open its eyes. Because what good is a universe full of stars if no one ever looks up? What good is symmetry elegance, curvature if nothing ever feels it. There's a phrase in physics, the observable universe. But that phrase is misleading. It implies that the universe simply is, and we happen to peer into it. But perhaps the better truth is this. The universe is observable because we observe it. It is felt because we feel it. It is named because we name it. It echoes with structure because something in us hears the echo. Even the questions we ask shape the terrain of answers we find. What does that mean? It means the search for reality is not a journey through space. It's a mirror. When you ask, what is gravity? You are also asking, what is presence? When you ask, what caused the Big Bang? You are also asking, why am I conscious of beginnings? When you ask, are we alone? You are also asking, am I alone? And when you ask, what is the universe made of? The real question, the one that echoes across centuries is, what am I? That's what this was always about. Not equations, not particles, not string theory, or brains, or bouncing universes. Those are just ways we've tried to say, there's something here, and I don't understand it, but I feel it. That feeling, that resonance is the real mystery. That a mind like yours, made of quarks and decay and stardust, can ponder infinity, can fall into awe, can weep over the silence between stars. Why? No theory fully answers that. No equation captures the feeling of wonder. But maybe that's the final truth we're circling. Maybe the deepest law of the cosmos isn't about symmetry or entropy or even information. Maybe it's this. The universe wants to be known. And to be known, it gives rise to knowers, to tiny conscious agents, to eyes that look up, to minds that ask, to hearts that feel the scale of it all and keep going. In the end, this journey wasn't about learning facts. It was about feeling scale, feeling the depth of our ignorance, and still daring to lean forward. So if you're left with questions, good. If your head feels cracked open, perfect. If you feel more small, more uncertain, more alive, you've understood. Because the point was never to explain everything. The point was to awaken you to how much more there is. And maybe to leave you with just one final question, softly whispered, quietly unresolved. What will you do with your moment inside this unfolding universe? Will you chase truth? Will you create beauty? Will you offer kindness? Will you stand in silence and listen? Whatever you choose, know this: you were here. The cosmos knew itself because you existed.